Welcome students, welcome to this lecture series on VLSI design KEC 072. This is lecture number 14. I am Dr. Raman Kapoor from ABS Engineering College, Ghaziabad. Today I am going to start a very important topic as part of this course, which is sequential CMOS logic circuit design. Okay. Before we proceed and initiate this topic, we need to understand a few things. The most important aspect which a VLSI designer should keep in mind is that at what level the design is being conducted. Okay. There are several levels, depending upon the interest and expertise, different people design at different level. This is known as the so called hierarchy in VLSI design. Okay. If I try to describe this hierarchy in the most general form, the lowest level or the highest level of detail in this hierarchy is the material itself, which is being used to produce these semiconducting devices. Okay. So, you can start with silicon or silicon germanium alloys. That material level properties of silicon, say roughness, absorption and different material properties, those are one level of hierarchy which is at the lowest end, okay, and has highest amount of detail. You can use that silicon to produce a device, okay, the MOSFET. The MOSFET itself can be used to produce a circuit. The circuit can be used to produce a logic gate. Logic gates connected together will give you a module, and several modules connected together make a system. Okay. So, if I try to draw this hierarchy, you can have a system at the top end. The system can be consisting of different modules. Okay. Modules have different gates, say logic gates. Okay. These logic gates were made by some circuit, okay, and this circuit came from some device, and the device itself was made up of some material. Okay. So, in this hierarchy, till now we are oscillating between logic gates and some circuits. Okay. We have done few examples, we have done static CMOS, we have done dynamic CMOS, we have calculated delays in circuits. Okay. In these, we are basically analyzing different types of logic gates, say universal gates, NAND and NOR, and taking example of inverter wherever necessary. Okay. Now, when we proceed further, we need to go one level up in the hierarchy. Okay. So, now I want to use these logic gates and design or at least understand some kind of a module. Okay. And this module itself is going to be performing some predefined or pre-explained function. Okay. So, sequential logic circuits are very common type of circuits. Most of the practical circuits are sequential in nature. They may be, the sequence may be synchronized, the sequence may be asynchronous, okay, but there is some kind of a sequence to the operation involved in logic circuits. Okay. Till now our analysis has been restricted to combinational circuits. The input to a combinational circuit is always present. Whenever we want, we can process the circuitry inside the combinational block and get the output. The input which is present at the time of processing is only considered. There is no role of the past inputs. Okay. There is no concept of memory, there is no concept of sequencing or clocking. Okay. So, combinational circuits are very simple and straightforward, but they from the practical point of view, from the operational point of view, okay, they have certain limitations. Although, for every sequential circuit you need at least one or more combinational blocks. Okay. Sequential circuits differ largely from combinational circuit in terms that they depend not only on the present input, they also depend upon the past inputs. So, some inputs which may have been applied to the system in the past, okay, what was the effect of those past inputs on the output at that time, that output is taken as a feedback, okay, and whatever present input is there, that is also used to generate what is known as current output. Okay. Most of the practical circuit, as I have said, are sequential in nature, they use clock, they use memory. Okay. A small bifurcation is given for you. Logic circuits can be it is such a wide field that you can have n number of classifications. With reference to the analysis here, you can divide logic circuits into two broad categories, combinational and sequential. Combinational are also known as non-regenerative, sequential are also known as regenerative. Okay. Sequential circuit further can be classified to bistable, monostable and astable. Okay. So, first major thing which we need to understand, that sequential circuits are going to be dependent upon previous inputs and outputs, and because they are dependent upon past data, that past data has to be preserved somewhere. Okay. So, you need memory elements also. That is why combinational circuits are also known as memoryless circuits, okay. And sequential circuits are known as a combinational block with memory, okay, and a clock. So, these bifurcation, as the name suggests, bistable sequential circuits are those circuits which are stable at two different values, and since we are talking about digital circuits, okay, the broader category of our analysis is digital VLSI design only. So, the two states which we are talking about are logic 0 or low state and logic 1 or high state. Okay. So, a circuit which when is giving you 0 as output and that output is stable, and that circuit at some point is also giving you 1 as output and that output is also stable, that is a bistable circuit. A monostable circuit on the other hand is only going to be stable at any one of the logic values, either it is stable at 0 output, or if the output is 1 and that is stable, okay, that means it is a monostable system. An astable system is the one which is oscillating, which is not stable at any logic value, it keeps oscillating between 0 and 1 and is difficult to reliably say whether the output is a 0 or a 1. Okay. One thing is common between bistable and monostable systems. A bistable, though it has two stable states, a monostable system has one stable state, but if you disturb these systems, by disturbance I mean if you apply a small pulse to excite the system, to trigger the system is going to eventually come back to one of the stable states. If it is a bistable system, it is going to come back to 0 or 1. If it is a monostable system, it is going to come back to its stable state, either 0 or 1. An astable state on the other hand will not give you any stable output, it keeps on oscillating without settling into stable mode. Okay. So, let us see how a sequential circuit looks like or works like. You need a combinational block, okay. You always need a combinational block, it can be your logic gates, it can be a adder, subtractor, counters, multiplexers, whole lot of combinational logic circuits you can design. You can implement a Boolean algebra using combinational logic. That combinational logic, if you do not have any clock, any memory, is a pure combinational circuit. Use that combinational logic, take the output and store it somewhere, okay. Store that output somewhere so that it can be used at a later stage. So, at any time t, if you are trying to calculate what is your output, that output is dependent on what is being applied at the input, present input, and it is also dependent upon current state of the system. What is the current state? What state the output or the system is currently exhibiting? That current state plus the present input, okay, is being used to obtain the present output, right. And when we say current state, now this current state is actually coming from some of the previous output. Okay. What is next state now becomes current state after some time. What is current state now was the next state some time ago. Okay. And what is next state now will become current state after some time, which basically means that indirectly your system is also dependent upon past inputs, because the value of this next state was obtained using some previous input. Okay. So, the effect of previous input is also taken into account and the present input is always there as application. Okay. This is the most general form or a general way how you are implementing a sequential circuit, and this storage is being triggered by a clock also. So, this current state will always not be available, it is like an on demand thing. Okay. So, whenever you need a value at current state, you have to synchronize the clock in such a way that when output has to be calculated, the clock triggers and send you some current state value. So, you take the effect of both present and past input and obtain what is known as the present output. Okay. The data in combinational circuit is always there, it is always present at the input. In a sequential circuit is generally presented sequentially, bit by bit, that is known as serial interfacing, and in some cases it is also presented in a parallel way, which is known as parallel interfacing. Okay. But the triggering is controlled. Okay. It is not that as soon as your input changes, the output toggles or changes. Okay. That is not the case, right. And depending upon the memory elements, if you can classify memory elements into different categories, that basically become the category of a sequential logic circuit. Now, that is one of the advantage, right. So, your input can remain active for a long time, but the output only changes when you want it to, depending upon how you have set the clock, right. In addition to that, propagation delays, which is the delay which takes for a signal at the input to propagate towards the output, that is always there in a combinational circuit. Since you use a combinational block in a sequential circuit, that propagation delay is always there, plus you have a few more parameters involved. Okay. One is sequencing overhead. So, once you have a large amount of data and you are sequencing it serially. Okay. So, if you are serially entering the data, it is entered through storage blocks, which are also called as flip flops. Those flip flops are nothing but a collection of logic gates only, and every gate has a capacitive action. There is going to be a cycle of charging and discharging. So, data takes some time of some extra delay to sequence through. This is known as sequencing overhead. Okay. So, this is an extra added overhead in a sequential CMOS circuit. You require additional circuitry because you have to store the data, you have to apply a clock. Both of these things require additional circuitry, but functionality increases, user control increases, you can parallelly interface data, a large amount of data is available at the same time, okay, and that can be propagated through. A lot of practical application rely on how sequencing is done. Okay. The separation between your past, current and next state of the system, what the system was displaying in the past, what it is currently displaying and what it might display in future. These things are controlled by approaches like either FSM, which means finite state machine, which is nothing but a sequential circuit which can exhibit finite number of states at the output, or pipelining. These two topics will be discussed at some point of time. So, let us proceed further. The most common approach of sequential circuit is what is known as FSM. As I said, FSM stands for finite state machine. Every word has a meaning. Finite means there is a limited number of something, and what something, the state of the machine, and machine means the sequential circuit. So, any sequential circuit which exhibits a finite number of values or outputs can be considered to be an FSM. Okay. So, the output of the FSM in the most simplest way form are dependent on current input and current state. Now, some type of circuits, they are also dependent only on the current state and may not depend on the output itself may not depend on the current input, but the next state will depend on the current input. Okay. So, the next state is determined based on the current state and the current input and is fed via an inputs of registers. On edge triggering means some kind of a pulse, which is your clock pulse. Whenever it changes its polarity, whenever it changes its edge, either 0 to 1 or 1 to 0, that is edge triggering, the next state is updated. and a new cycle begins. Okay. This will be discussed in more detail very soon. The register or the storage element is then becoming independent. Once the next state is updated, the registers do not become active until your next cycle arises. Okay. So, any change might happen at the input in this time, but that is not reflected in the next state. So, that is why we said that sequential circuits allow more user control as compared with combinational circuits. Now, since we are talking about clock and memory and triggering and pulses, there are a lot of timing issues associated with sequential circuit. A well designed sequential circuit will always take into account all the timing overheads. Okay. Suppose you have applied one particular input and you have to wait for some kind of a trigger, which is generally given by the clock. That trigger, until that trigger comes, some time should have elapsed and the input should remain active or should remain available for a small amount of time before you can actually do some processing with it. So, that time is known as setup time, the time for which the input should be available, the input should be valid. Okay. By valid we mean that it should be holding a particular value either 0 or 1 for some amount of time, okay, before your clock transits. Right. So, that if a trigger is coming and the input is also very short lived, that might result in unreliable operation. So, the input must be present for some amount of time before clock arrives or clock triggers. That time is known as setup time, and once clock has triggered, that data at the input should remain valid for some more time, okay, and that time is known as hold time. So, before clock triggers, the input should be remaining there, then input should be valid for some time, that is your setup time. Once trigger has happened, again the input should remain valid, should remain available, so that data transition is considered as reliable, that is known as hold time. Okay. With respect to clock or the clock edge, you can describe what is known as worst case propagation delay. Propagation delay is nothing but the maximum time it takes for the output to become steady once input has changed. So, your starting point is when input makes a transition. From that point until output becomes steady, that is a propagation delay. Okay. In addition to that, you have contamination delay, which is actually the minimum time. So, if propagation delay is the maximum time it takes for the output to become steady after input has changed, contamination delay is the minimum time when the output actually starts to make a move. Okay. So, suppose at time t equal to 0, your input changes, a finite amount of time will lapse depending on the circuit complexity when the output starts to make a transition. That minimum amount of time is known as contamination delay, and the maximum amount of time or delay it takes for output to become steady, that is your propagation delay. So, in a sequential circuit, you can define propagation delay either with respect to the clock or with respect to the input. In a combinational circuit, there is no clock present. So, the propagation delay is only measured with respect to transition in the input. In a sequential circuit, you can define propagation delay or for that reason contamination delay also with respect to the input. Okay. But since clock is also acting like a trigger, you can define propagation delay as well as these contamination delay with respect to the clock also. Okay. So, suppose input makes a transition at a different time, but clock triggers. So, with respect to the clock also you can define these delays. Okay. So, these are some of the timing parameters. Number 1, setup time, the time for which input should be valid before clock triggers. Hold time, the time for which input must be valid after clock has triggered. A propagation delay with respect to the clock, a propagation delay with respect to the data input. Okay. Contamination delay, the minimum amount of delay when output starts to change after input has transited. So, this timing diagram sort of explains further the timing parameters associated. Okay. So, this is your clock cycle at the top. Okay. So, it is going 0 here and 1 here. Okay. Data here makes a transition. This point here is your point of transition. Okay. Until the clock triggers, the data should be valid or available for some time. Okay. It should not change at that time. This is your setup time, and after clock has triggered, it should still remain, so that all delays can be accommodated. This is your hold time. Okay. And this T C Q is your contamination delay with respect to data. Okay. Sorry, this is with respect to the clock. When the clock triggers, how much contamination delay is there. Okay. So, there are some unstable states here, and then data output becomes stable, right. So, the timing constraints which are generally associated, the clock time period. So, here uppercase T represents the clock period. Okay. TP logic represents your propagation delay with respect to data input. Okay. Then setup time. So, your contamination delay with respect to the clock, propagation delay with respect to the input, and your setup time. Add these three, the time period of the clock should be at least equal to this number. Okay. So, setup time plus contamination delay with respect to the data output or clock, plus your propagation delay with respect to your data input when data changes. Okay. These three time period put together should at least be equal. So, your clock time period should at least be equal or preferably exceed this time. Okay. And your hold time should be less than or equal to the contamination delay with respect to the output, okay, plus contamination delay with respect to the input. Okay. So, these two time values added together, the hold time should be less than or equal to that. Right. So, these two timing constraints are the most basic constraints which a sequential circuit should satisfy. Okay. Let us discuss these memory elements. Okay. Sequential circuits, if you remove memory from that, you are nothing but left with a combinational block only. So, a large basis of classification of a sequential circuit is what kind of memory you are using. A memory that is embedded into logic is known as foreground memory. Okay. It is one of the most organized way, or it has individual registers forming a register bank. Large amount of centralized memory core are referred to as background memory. So, a system with background memory can be called as a background sequential circuit. A system with foreground memory can be considered as a foreground sequential circuit. Okay. Background memory has arrays, so more higher area density, but then the performance and robustness is reduced. Right. Static versus dynamic memory. This is the most common classification of memory element in a sequential circuit. So, many times there is a small confusion that combinational circuits are static and sequential circuits are dynamic, while sequential circuit can also be both static and dynamic depending upon what kind of storage mechanism is being used. Static memories just preserve the state as long as you have power turned on. They are built using positive feedback or regenerative feedback. Circuit topology consists of some connections between the output and input of the combinational circuits. Okay. This is known as static memory. A system, a sequential circuit which uses this type of memory is a static sequential circuit. Dynamic memory on the other hand uses capacitive mechanism. Okay. So, data is stored as charge on a capacitive circuit which is continuously refreshed to avoid discharging. Any sequential circuit which uses dynamic memory is a dynamic sequential circuit. Okay. They are quite useful, more often used than static memories. Now, let us differentiate between a very common topic which we encounter, that what is the difference between a latch and a flip flop. The data is being stored to obtain the current state, so that next state can be defined. So, data is being stored or latched somewhere. But what is the difference between a latch and a flip flop? both are considered as storage elements. Okay. They are largely the same, they are used for storage in a sequential circuit. The so called memory element of a sequential circuit is a collection of latches or flip flops. Okay. The difference being a latch is level triggered while a flip flop is edge triggered. Okay. So, a flip flop can trigger with a pulse, a latch will trigger as long as enable is active, right. When a latch is enabled, the output changes as soon as input changes, but the output of a flip flop remains constant after triggering, pulse triggering or edge triggering, even if input keeps on changing, right. And every flip flop requires a latch for its construction. Okay. So, this is major comparison between a latch and a flip flop, and just see how latching works. Okay. So, latch operates in two different modes. One is known as a transparent mode. This is your writing mode basically. So, when the latch is enabled, whatever you have applied at data input D gets copied to data output Q. These are standard notations. Input is generally represented as D and output as Q. Okay. So, when we say clock signal is high or enable is high, you might implement a clock with a latch without a clock also. You can use a simple enable switch, enable pin, which can be active high, active low. Okay. If it is active high, which means enable is high, logic 1, data will be written to the output. If it is active low, means when enable is at logic 0, data will be written to the output. Okay. So, this is what is known as positive latch and negative latch. When the clock or enable is inactive, okay, opposite to what it was in the transparent mode, the latched output is held stable for the entire phase. Okay. So, until you have the correct level on the clock, positive for positive latch, low for negative latch, until you have the correct level, data will be keep on writing at the output. As soon as the enable or clock reverses, the data becomes held, latched and remains stable until the next level triggering occurs. Okay. So, major difference being that a latch can work without a clock, but it still needs an enable signal, and that enable is level dependent, it is not transition dependent. Okay. So, as soon as the correct level is available at the enable or clock, data as soon as input changes, output will get refreshed, of course, after some finite propagation delays, but that activity will keep on going. That is a major difference between a latch and a flip flop, but the latching operation is also common in a flip flop. Latching of data is also happening in a flip flop also, we will see later on, but the mechanism or how the triggering is taking place is different. Okay. So, with this we come to the end of this lecture. I have given you a brief introduction and an overview of sequential circuit design. What are sequential circuits, how they differentiate from a combinational circuit, what are the different advantages, what are some of the limitations. It requires extra circuitry, it requires memory, it requires synchronization, sequencing. Okay. But all these limitations are very small when we see that a better user controlled and more functionality is provided by sequential circuits. In the next few lectures, we are actually going to see implementation of how sequential circuit is designed and implemented. Okay. Thank you.